Hey muchachos and muchachas, today I'd like to talk to you a little bit about how to work with sound files in Matlab. You may be thinking, well, why would I want to use a sound file in Matlab? That's not a sound processing package. Sure it is. Sound files are just data. Matlab works with data. Matlab doesn't care that that data happens to be a sound. Okay? So what I'm going to show you here is how to take a sound file that's saved as a WAV file. We'll pull it into Matlab, we'll plot it, we'll play it, and we'll modify it. Alright, so here we go.
Okay, here we are in Matlab, and I've got a file over here called acousticguitar.wav. And all I did was take one of my guitars, I don't remember which one. I have a guitar lab here, so I got a lot of guitars. And plug that into a recorder or a computer or something, and recorded a little chord progression from an old folk tune by James Taylor. And you're about to see why I'm doing Matlab videos and not touring as a guitar player. So if I want to pull this into the workspace so I can work with it, the easiest way to do it is hit right click and go import data. Oops. So it's going to come in with the file, the variable name data, and the sample rate. It's going to be 44,100, and the sample rate actually lives inside the header for this file. There's some header information, and then there's the sound information. And so I want that sample rate. I'm going to need that later. So there it is. My sample rate's 44,100. I picked that because that's CD sampling rate. If you have CDs with music on them, they're sampled at 44,100 samples per second. Alright, so what can I do with that? That's just data. Matlab does not care that this is music. It just knows it's data. Can I plot it? Sure. Let's do that. So there it is. I'm going to blow this up a little bit, and parts of this look pretty suspect. I don't quite remember how I did this, but see how none of those points go any higher than that? That sure looks like clipping. That sure looks like I clipped the signal, probably going in when I recorded it. WAV files are normalized so they go between plus and -1, and they are not compressed. MP3 files are compressed. They throw information away to make the file smaller. WAV files are just raw numbers. The only thing about them is that they are normalized to plus and -1, and the volume, basically the multiplier, lives inside the header. So let's just take a peek here. Let's maybe go in right there and take a look. Zoom in. Let's zoom in there and zoom in. Oh, look at that. Yeah. That's what clipping looks like. It's very unlikely that the recording, the sound actually made a flat peak and then went down again. That's not likely at all. What's more likely is that I had a voltage limit while I was recording and I clipped the signal on the way in. That's what clipping looks like. And when you look at signals in time domain, let's zoom back out. Anytime you see something that looks like that, yeah, that sure looks like clipping. Boy, it sure looks like I messed it up coming in. But that's why you buy recording equipment and don't just plug your guitar into your computer like I did. But that's okay. This works fine. So yeah, that's what clipping looks like. So I've already been able to tell something about the file just by looking at it. Now, I don't know how well you could hear this on this recording. I'm not sure how good my screen capture software is at capturing WAV files that I play, but you'll eventually hear that right there. See that stuff? That's going to be, it sounds like me scratching my fingers against the strings a little bit before I started playing. I can hear it, and hopefully you will too. There's something else interesting. See that? See how it looks like everything goes up and down in steps? Well, it does. This is a digital signal. Okay? There's a finite number of vertical, numbers along the vertical axis that it can distinguish. And there they are. See that right there? That is delta V. That is the smallest change in voltage I could resolve with this recording. Now again, what this means is I kind of biffed it on the way in. A good recording system, you should be able to, the delta V should be so small you can't see them. But actually, it's kind of by accident, but it's actually fortuitous that we're able now to see there's delta V. There's what delta V looks like. If you want to tell quickly whether you've got what this is called discretization error. It means your discrete voltages are so big that they're actually observable and they actually change the signal a little bit. Let's do this. Plot, and let's sort. There you go. Sort the data file. See that? That's what sound data looks like, what oscillatory data looks like when you sort it. What should be happening, see those steps there? Those should be way too small to see, and they're not. Let's try something here. Let's put a marker on that right there. Okay? Now, see how many markers are there? That wasn't just one. There wasn't a data point there, and over here. There's a lot of data at this delta V. There's tons of it. See how far I'm having to zoom in to see it? Okay, so that means there's during that sound recording, there's lots and lots and lots of data points at that single delta V. Well, that means probably my delta V is too big. I need a smaller delta V. So right there, that's what discretization error looks like when you sort your data file. If you can actually see these steps, those steps are too big. That means you've probably got a problem. All right, well, that's good. We've plotted it. We've observed something about the file, the data that came in. We've actually been able to learn something about how well it was recorded. What does it sound like? Can you play sounds in Matlab? You bet. Sound SC is sound, and the SC stands for scale. What it does is it scales the volume. There's the file I'm playing, and there's the sample rate. So I'm going to play it here, and it's going to come out through, actually come out through my headphones here on the screen capture, and I think you'll be able to hear it too. If it's faint, I will gain it up during post-processing of the video. All right, there you go. That was sound played through Matlab. Now, can I modify that data vector in Matlab? Sure, you can modify any data vector in Matlab. It doesn't matter whether it's sound or not. Matlab doesn't care what that vector means. To Matlab, that's just data. Doesn't care where it came from. Well, I checked out earlier, and it looks like the first 82,000 points in the file were me accidentally dragging my fingers along the string when I probably shouldn't have. So let's try something here. Let's not play that first 82,000 points. So this says play from 82,000 to the end. Now what happens? And maybe not to the end. Let's skip the last 100,000 points, because that was just decay. Okay, but that last 100,000 I chopped off a little over 2 seconds, 2.5 seconds of data. Well, could I play that faster or slower? Sure. Now I don't want to play too much of it here. Let's play 2 seconds. 180. Well, here, let's do this. 82,000. Yeah, let's get clever about this. Let's call X data 82,000 to the end minus 100,000. I'll just clip a little bit out of the middle of this file. Okay, now definitely hit the semicolon. You definitely don't want all those points echoing to the screen. That's 100,000. Okay, there. See there? X is now my shortened file. I got rid of some of the stuff at the beginning I didn't want to listen to, and some of the stuff at the end I didn't want to listen to. Well, let's maybe listen to, I don't want that. Let's do this. Let's listen to the first 2 seconds. I'm going to do that wrong here. Hang on a second. There we go. That looks better. Let's listen to the first 2 seconds of data. 2 times the sample rate will give me 2 seconds. And let's listen to it at twice the sample rate. What does that sound like? Sounds like Alvin and the Chipmunks, right? Maybe listen to it just a little bit, not quite that fast. Could I listen to it slower? Yeah. Okay. This is an interesting tool we can use here now. When working automotive noise and vibration problems, I routinely listen to accelerometer data using the sound SC command. If the accelerometer you're using is sitting on a vibrating piece of equipment like a car brake or an engine or an intake or some of the things we used to work on at the company I worked for, you could slow accelerometer data down and listen to it, and you could hear things that were difficult to see in plots. Remember, Matlab doesn't care where that data came from. It doesn't know that it came from a guitar. It doesn't care if it came from that or an accelerometer. You can listen to anything. Now, one last thing before we sign off here. This is an AC signal. It's an oscillatory. Could we calculate the root mean square of this? Sure. Okay, root mean square. Well, let's build it from the inside out. Root mean square. So the first thing I have to do is square the signal. Okay, there's the signal squared, and I have to use the dot there because I want to vectorize this. I want to work on the elements of the x vector one at a time. I need the mean of those. Well, there's a command called mean, and I need the square root of that. Root mean square. There's the root mean square of that signal. And just to double check, let's just do a sanity check here. Let's plot x and see if it looks like RMS could be about 0.224. Okay, lots of stuff. Yeah, that could well be. There's lots of content in the plus minus 0.2 range, so that could well be the right answer. So there you have it. We've pulled in a wave file into Matlab. We've looked at it. We've listened to it. We've modified it. And we've calculated the root mean square. Hope this helps. I'll see you next time.